Today we're going to talk about molecular structure. It's in Chapter 9, Section 3. Structures. We just learned about names. After structures, we'll learn about shapes. And then you'll know everything you need to know about covalent compounds. So there's a few different kinds of structures that we can do, a few different models we can do. We can look at a stick model, where they don't show any of the little atoms, the nucleus, they just show where the bonds are and the shapes there. There's a ball and stick model, which shows both nuclei relative shape or size. It shows relative size of the atoms. So you'll notice like the white balls are a little smaller than the gray because these are hydrogen, the gray are carbon. And then molecular structure, you can also fill the space completely, which is probably the most realistic model, because we know they all have clouds of electrons. And then this space-filling model shows the entire area that the electrons and the nucleus will take up. So those are the three different types of models you should know about. So we talked in an earlier lecture about, or guided instruction, direct instruction, about some of these Lewis structures. You've done some of these. You've done water. You've done, this is methane, and this is ammonia. But this H2SO4, this is pretty tricky. And so we're going to talk more about what do you do when you have something really tricky like this, where there's more than one central atom. See, this has one central atom. This has one central atom. Ammonia has one central atom. That's pretty straightforward. So how do we do it? I'm going to go through 5 basic steps that you can follow every time to make these structures. First step, know that hydrogen is always going to be terminal. That means it's going to be the end of the chain, the end of the line. Why is hydrogen always the end of the line? Because it only has one electron to share and one electron that it wants. So it can only ever have one bond. So, second part, your lowest electronegativity is always your central atom. And remember, who is the most electronegative? Fluorine. So if fluorine's the most electronegative, whoever's farthest from fluorine is going to go in the middle. C4H8O2. Write this in your notebook. Write that formula. C4H8O2. And then we're going to draw the structure for C4H8O2. And if you can do that one, you'll be able to do any of the ones in your book, because I generally won't ask you to do one this complicated. Okay? So, hydrogen, we know it's got one electron. Carbon is 2.55 electronegativity. Oxygen is 3.44. We didn't really even need to look that up because we know oxygen is closer to fluorine, so it's more electronegative. We learned that in Chapter 6. You figured that out when you made your periodic tables. Now that we know carbon's going to be in the middle, the second step is finding the total number of bonding electrons. Now, some of you could just start drawing, and that would be fine. But you always want a way to double check. And so this is how you double check your math problem or your structure formula. You need to add up total number of valence electrons. Wow. That's not that hard. It's pretty basic math. How many valence electrons does carbon have? Hydrogen and oxygen. Hydrogen has one valence electron. You have 8 hydrogen, so that's a total of 8 valence electrons. Does that make sense? Carbon has 4 valence electrons, so this is the number of valence electrons right here. Valence electrons. This is the number of actual atoms you have. You multiply and you find out total total electrons. So you have 8 from the hydrogen, 16 from the carbon, 12 from the oxygen. We're going to add those all up and find out how many total electrons we have. 36. If I have 36 electrons, how many pairs are we going to have? Because pairs are what make bonds, right? You need 2 electrons in each bond. So we're going to divide by 2 and get 18. 36, divide by 2. So you're going to have 18 bonds or lone pairs. And that's going to be your check. So when you start drawing, you can always go back and look and see, do I have 18 bonds and lone pairs? Because that's how many total electrons I have on the outsides of these atoms, and they all have got to be accounted for. So we did this, we did this. We found the total number of bonding electrons, we found the number of pairs. Now we're going to place one bond between central atoms and all the outer atoms. And we said the carbon was going to be the central atom. So we're going to put all the carbons in the middle. So I put all the carbons in the middle. I mean, you could draw your chain going horizontally if you want. But I put all the carbons in the middle. And then I put some hydrogens at the end here, and I put hydrogens at the end here. Again, you're never going to have to do a chain of carbons that is 4 carbons long. The oxygen, hydrogen, those could have gone on the outside. There's a lot of different possibilities from this formula. Those would be structural isomers. You would have different combinations. You could have put this oxygen, hydrogen over here. You could put them over there. I put them in the middle, or along the middle carbons. So we're going to put one bond. I'll put the bonds in place. So there's one bond to each of these hydrogens, carbon to this oxygen, carbon to this oxygen, and carbon to these hydrogens. Oxygen to this hydrogen. Again, you could have probably put a hydrogen right off of a carbon. But I'll show you why that actually wouldn't work out. So I put those oxygens on the outside of the carbons. It's not finished because, oops, if I go back, sorry, 5 pairs, we still have 5 pairs left. If I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pairs in the bonds. So I have 5 pairs left over. So let's start looking at who would have some lone pairs. I'm pretty sure oxygen always has lone pairs. I didn't expect them to draw the pairs first. So now if we put some lone pairs in place, oxygen has 1, 2, 3, 4. Because oxygen has a total of 6 valence electrons. Oxygen will always have 2 lone pairs and 2 bonds. Always. It might be a double bond, but oxygen always needs 2 more electrons, so it'll always have 2 bonds. Hey, wait a minute. We still have 1 pair of electrons uncounted for. How many lone pairs do I have in this molecule? 4. How many pairs? I figured out I should have 5. But I can't throw any more electrons around anybody. Who's not happy yet? Who does not have 8? Look through this molecule. Looks to me like this carbon here, he only has 3 bonds, which is only 6 valence electrons. And this carbon only has 3 bonds, which is 6 valence electrons. So we need to form some double, maybe triple. The last step, we're only going to need to form a double. Oops. Sorry. You've got a double bond right here between these 2 carbons. And that's where my last pair had to go. So if you follow these 6 steps with any structural formula, it'll never be as complicated as this one was. It'll work for you. Okay? The only difference is when you're dealing with polyatomic ion. I'll put those 6 steps back up. They're also in your book after we're all done. What if I have a polyatomic ion? Back when we learned the last chapter, polyatomic ions, I told you guys they have covalent bonds within them. So they are something that's covalently bonded. So this is a plausible thing I could ask you. So let's go through our 6 steps for these. The only difference is, what does this plus mean? Brock, why does this have a plus to it? Polyatomic, what did it have to do to end up being +1? Didn't it have to give up an electron? So what did this guy do? Sulfate, that's SO4 2 negative. So when I figure out my total electrons for ammonia, nitrogen is going to have how many? 5 valence electrons. How many nitrogens do I have? I only have 1 of them. So that's 5 electrons there. Hydrogen has 1 valence electron. I have 5 of them, so there's 5 electrons there. That would be 10. Oops, I have 4. My bad. How do you guys let me say that for so long? You had to jump on me and tell me, no, 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 Miss J, there's only 4, really loud. 4. So that's 4 valence electrons. That would be 9 electrons. But this positive means that we did what, Brock? Took the electron away? Thank you. So there's 8 electrons to work with this polyatomic. Who's going to go in the middle? Well, not the hydrogen, so that leaves nitrogen. Can never be hydrogen. Nitrogen, there's 4 of these. Nitrogen, 1, 2, 3, 4, 4. Hydrogens, 1, 2, 3, 4. How many electrons do I have in these bonds? Aren't there 2 in each one? Test, 2 times 4 is 8. 8 electrons. Happy, happy polyatomic ion. The only thing is you should put it in brackets and add a little plus sign so that we know really to do this structure we had to take away an electron. Sulfur, oxygen. Who's closest to fluorine? Oxygen. So sulfur is going to go in the middle. Total electrons. Sulfur has 6, oxygen has 6, so it's really 4 and 5 times 6 is 30. But it's got a 2 negative charge overall, so I have to add 2 more electrons. So I have 32 electrons. How many pairs is that? Divide by 2, I know I have 16 pairs now. Okay. Let's do this. Put sulfur in the middle, and there's 4 oxygens. One, 2, 3, 4. I said put a single bond between the central atom and the outer atoms. Okay, so that's done. But how many valence electrons do I have? I have 8. Sulfur's happy. But these oxygens are not happy. We're going to have to do something really weird here. You guys are going to get mad at me. We've got some lone pairs, right? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's still 4 more pairs. What does oxygen want to do? It wants to have 8 pairs. It does not have 8 pairs yet. Sulfur happy? Yeah, sulfur's happy. But what is, I got to show you the answer. It's the only way to really do this for you. I'm going to leave, that's all there. It's just going to look much prettier. So with those 4 more lone pairs, or 4 more pairs, you can just give one to each of the oxygens. What's really happening, Emily, is that oxygen's taking out 2 electrons from sulfur. Remember, oxygen is really electronegative. It pulls electrons quite a bit. So it pulls electrons away from the sulfur, and when it's pulled all that it can, it's going to pull 2 more from something else. How do we know it's going to pull 2 more electrons from something else? Because the polyatomic ion charge is -2. So it got 2 electrons from something else nearby. Drew, question? The lone pairs? If you go back to what we talked about when we first figured out structures, and if I were to just ask you, draw a Lewis dot structure for oxygen, and you would put 6 dots around it. 1, 2, 3, 4, 5, 6. All right? That would be the Lewis dot structure. Now I'm saying, hey, this oxygen's coming up against a sulfur, and they're going to form a bond. This oxygen is going to want to bond with the sulfur and take sulfur's electrons. So now we're doing these kind of things, where now we're drawing a bond and showing that they share in order to get that perfect 8. This one right here, this example in particular, is really hard. This one I hope you guys would be able to do, the ammonium. But the sulfur, that's pretty tricky. All right? This would be like bonus on the test if you could totally get this. The formula for sulfate is SO4. So there are only 4. And again, put them in brackets, give the overall charge once they're all done for polyatomic ions, because they're ions. They have a charge. So you got to tell me what that is. Okay, why don't you guys try these? C2H6, N2, CO2, and ozone. And ozone is bonus. It's tricky. The others I think you can do. Try it. Carbon has how many valence electrons? 4. Hydrogen, 1. Hydrogen always goes on the end, so the carbon's got to go in the middle. Put your carbons in the middle. And let's look at 4 times 2 would be 8 valence electrons from the carbon, and 6 from the hydrogen, and 6 plus 8, 14 total electrons, and 14 divided by 2, 8 pairs. Oops. Oh, thank you for catching me right away. Guess I should eat breakfast before I come to school. So we're going to put carbon in the middle. We're going to put hydrogens all around. And I have used 1, 2, 3, 4, 5, 6, 7 bond pairs. Carbon feels like it has 8. It's happy. All the hydrogens are there. You're done. How'd you do, Brock? Can you guys give me a thumbs up if you got that? Can you give me a thumbs down if you're still lost? Let's try nitrogen. You just keep trying to climb this wall. Eventually you will get up this wall. And then you'll be able to climb any wall there is. Nitrogen ends up looking like this, because each nitrogen has 5 times 2 of them, 5 valence electrons, and there are 2 of them. That's 10 electrons. Divide that by 2, that's 5 pairs. So something's not done here, isn't it? You need to have, it needs 3 more, and each nitrogen's going to get 3 more. You've actually already done this structure earlier in this chapter. You said nitrogen would need 3 more, and it had 5 valence electrons. So if I were to draw the electrons that are in these bonds, I could draw them like that, and you would say, hey, this is the very first structure we ever drew. You have to have the dots. These lone pairs you have to have. You do not need to show these dots that are within the drawing. You don't have to have those. I'd rather you didn't. You could draw them at first, Emily, and then connect your line, and they'll just look like they're part of the line. Why do I have to have which dots? These are lone pairs. This is a lone pair. Why did I get rid of those dots, these dots here? Why don't I show these anymore? Because they are part of that line. 2 points makes a line, so there's 2 points I'm going to connect between these nitrogens, and once I've connected them, I don't have to show the dots anymore. All right, but if you want to draw them on your structure, go right ahead, and then connect them, and they'll become part of the line, and I won't even see them. Nitrogen has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I had 5 pairs when I'm all done. That's a pair. 2, 3, 4. And that's a pair. 5 pairs. Lauren. You follow those steps we went through at the beginning where you figure out how many total pairs you have. Initially, I would have just drawn 1 pair, and nitrogen's not happy yet. And I still have 4 more pairs to get rid of. And so then I'd keep going like this, give it its lone pairs, and I don't know. You keep trying, you guys will get it. Carbon, this is not done. What's wrong with this one? There's 4 from here, 2 times 6 valence electrons here. So if I add that all up, 2 times 6 is 12. 12 plus 4, 16. Divided by 2 makes 8 pairs. Okay. I got to put carbon in the middle because it's farthest from fluorine. It's the least electronegative. And then the oxygens are going to go on the outside. I put 1 bond in between them, and carbon's still not happy. So I put a second bond. Now carbon is happy, but I only have 1, 2, 3, 4 pairs used up. I still have 4 more pairs left over. So I'm going to put a pair on the oxygen, another pair on the oxygen. And you and I both know, because we do Lewis dot structures all the time, we know that oxygen would have started out with 6 pairs anyway. So if I were to have drawn the 1, 2, 3, 4, 5, 6 electrons it would have had, it would have looked like that, and then it would have bonded with carbon. 2 electrons here and 2 electrons here. Always start with single bonds and see if your central atom is happy. If your central atom isn't happy yet, you're going to need another bond. You might need a double bond in here. Let me show you another problem. Let's talk about ozone in a minute. Can I show you? How about you guys draw C2H4? Oops. Well, 4 times 2, 4 times 1, 8 and 4 makes 12 electrons to work with. Divided by 2 means 6 pairs. Hydrogen's always going to go on the outside. Carbons are going to go in the middle. But now I only have 4 hydrogens. And how did I know to make this even? Practice. Put a bond between carbon. Carbon's not happy yet. And I believe I have 1, 2, 3, 4, 5 pairs. Drew, I've only used up 5 pairs. I have 1 more pair left. And are these 2 carbons happy? They're not happy yet, are they? Because they want 8, and they only have 2, 4, 6. So I'm going to put it, now I know I got to put a double bond there. It's the only way to solve this problem. It's always okay to do things vertically, diagonally, horizontally. I don't care. Just do them right, and I will be so happy. And the last thing we need to talk about, as Breslin is reminding me, is the ozone. And ozone is a little quirky. Ozone is super cool. It has what's called resonance. So we need to talk about resonance. Here's ozone. I'm going to pass around a Jacob's ladder, which is a good example of an ozone molecule, because you could draw it with a double bond on the right, or you could draw it with a double bond on the left. And that means that, like Jacob's ladder, ozone is really good at absorbing energy. So when I apply energy or kinetic motion to it, the molecule vibrates. And if you look, there's like double bonds, and a single bond, and a double bond, and a single bond. And if I flip it, the double bonds flip to the other side. So there's double bond on the top. There's no bond on the top. There's a double bond here. There's a single bond. Double bond, single bond. And ozone absorbs energy, like ultraviolet energy, that way. So we'll pass this around. It's an example of bonds, single bonds and double bonds flipping. That is called resonance, right? That's one of your key terms. There are more, but basically it means that there are multiple Lewis structures that are correct. There's more than one correct Lewis structure you could draw. Yeehaw. So if I do that again, watch. You switch that double bond into a lone pair. That's correct, and that's correct. Those are both correct. Will. Yeah, I can keep going all the way around this molecule. No, I have to have no dots. I have to have the lone pairs. These lone pairs, you can't just take those out. You can, but not for this chapter. For this chapter, you have to show me you know they're there. But absolutely all the time, biochemists draw their oxygen molecules. They don't show all the electrons around them. But I need you, this chapter, to show me that you can do this. Oh, forgot to mention. So you can draw, and what you'll see in organic chem books when you take organic chem, they draw resonance bonds with little dashed lines to show you, hey, we could have a double bond to here, here, or here. So here's another chance to show some resonance structures. Again, the ozone, you could draw the little dashed line. Sulfur, draw the little dashed line to show me multiple bonds could go over here or it could go over here. And like Will wanted, I didn't even show the lone pairs on these, although you really should. The last thing are the exceptions, and these are total bonus if you can get these on the test. Some of them are pretty straightforward. They make sense. If you look at boron, he has 3 valence electrons. And so if he's going to combine with hydrogen, all they can do is share 6 electrons. That only makes 6 electrons around that central atom. And that doesn't follow our rule of 8 is great. It's an exception. That's as happy as that boron can get right there, to have fewer than 8 electrons. It's also possible to have expanded octet. This sulfur has 2, 4, 6, 8, 10, 12. You don't have any choice if I've given you 6 fluorines around a sulfur. These things happen once in a while, but they're exceptions. So again, they're not going to be something I'm going to definitely expect you to know, except to know that they're out there. They exist. They happen. But we're not going to draw them on a regular basis. Oh, last vocab term for this section, coordinate covalent bonds. I actually showed you a couple coordinate covalent bonds, but I didn't point them out to you and name them. Coordinate covalent bond just means that both the electrons came from one atom. So, for example, this bond right here. Boron only has 3 electrons to share. Hydrogen only has 1. So how the heck is there a bond here? The only way there could be a bond there, because boron has shared its 3 with those hydrogen, is if nitrogen, which normally has a lone pair right here, gives both of its electrons to the situation and shares both of his electrons so that he can say, I've got 8, and boron can say he has 8. Question, Jeffrey? They don't need a double bond because they have, nitrogen has 4 and boron has 4. But what the coordinate covalent bond is saying, the term means just that this nitrogen has donated both of its electrons to this bond. So this bond is a coordinate covalent bond. That one right there. And that's it for 9-3.